All right, so let's go over some questions from line structures. Okay, now if you look at this problem over here, right? So we are given a line structure now, and then the question is asking about the bond angles. Okay, 1, 2, 3, and 4. The first thing you do when you are given a line structure is to convert that to a Lewis structure. Okay, so if you do that, let's see if I can take a screenshot here. Okay, so in a line structure, all the ends and bends are carbon atoms. So the first thing I would do is to convert all my ends and bends into carbon atoms. So here we have an end over here, so this should be a carbon. And then let me see if I can increase the that's fine, carbon atom over here, and here is a band, carbon atom, band, carbon atom, carbon, 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 and carbon. Okay, and once we replace the ends and bends with the carbon atoms, we need to make sure that our carbon atoms have 4 bonds around it. That means it has fulfilled its common bonding pattern of 4. So for an example, if you take this terminal carbon over here, we only have 1 bond. Therefore, we need 3 more bonds to complete the common bonding pattern. So we add carbon hydrogen bonds to complete the common bonding pattern. Okay, so we need to add 3 carbon hydrogen bonds to complete the common bonding pattern of that carbon. Here we only have 2 bonds. Okay, we need to have 2 more bonds, and that comes in terms of carbon hydrogen bonds. Same thing over here, and same thing here. And then there are 3 bonds on this carbon, so we just need 1 carbon hydrogen bond. And this carbon has already 4 bonds, so we don't have to do anything about that. And here we have only 3 bonds around it, so we need to have 1 carbon hydrogen bond. And then on this carbon we have only 3, we need 1 carbon hydrogen bond, 1 carbon hydrogen bond here, and 1 carbon hydrogen bond over here. Okay, and that takes care of all the carbon atoms. And then to make it a complete Lewis structure, we need to make sure that we have an octet around all the elements except for hydrogen. Okay, and if you look at the nitrogen on the right here, we have 3 bonds around it. That means 3 bonding electron pairs, so 6 electrons. It does not have an octet, so we need to for it to have an octet, we need to add a lone pair. We need to add 2 more electrons in terms of a lone pair, and then if we do that, you're going to see something like this. Okay, and then there's one other nitrogen atom here. We only have 3 bonds on the left nitrogen atom. We only have 3 bonds. That means 6 electrons. We need 2 more electrons. Therefore, we need to add 2 more electrons, like in terms of a lone pair, so that nitrogen will have an octet of electrons as well. Now we converted our line structure into a Lewis structure. Now we can easily determine the bonds. Okay, so let's start with the first bond angle. Let's see if I can do something here. Oh no, let's do that. Okay, so what I want to do now is to determine this bond angle 1 now, right? So we have this carbon over here with 4 electron domains around it. All of them are bonding electron domains. If we have 4 electron domains, that means the electron domain geometry is tetrahedral. And because all of my electron domains are bonding electron domains, the molecular geometry is also tetrahedral. If you have a tetrahedral geometry, then the bond angle is going to be 109.5 degrees. So bond angle 1, in this case, this guy should be 109.5 degrees. Okay. And the bond angle 2, again, we have 4 electron domains around it. One lone pair is an electron domain, and then we have 3 single bonds. They have 3 electron domains in terms of 3 single bonds. So altogether, we have 4 electron domains. And whenever we have 4 electron domains, the electron domain geometry is tetrahedral. And when it comes to the molecular geometry, we only look at the shape of the molecule. The shape of the molecule must be trigonal pyramidal. And if you have a trigonal pyramidal geometry, the bond angle, talking about this bond angle over here now, this bond angle must be closer to 109.5 degrees. So it's going to be about 109.5 degrees. And because the lone pair takes up more space than the bonding electron pairs, this bond angle will be a little bit pinched. Therefore, it should be a little bit less than 109 degrees. Okay, let's write that here. Should be less than 109.5 degrees. Okay, and the bond angle 3. So this carbon over here, okay, has 3 electron domains, 1 single bond, 1 double bond, actually 2 single bonds, and 1 double bond. That means 3 electron domains. Therefore, the electron domain geometry must be trigonal planar. If we have a trigonal, and also the bonding, because all of these electron domains are bonding electron domains, the molecular geometry is also trigonal planar. If you have a trigonal planar geometry, the bond angle must be closer to 120 degrees. Okay, so this bond angle over here must be about 120 degrees. The last one, the bond angle 4. What we have here is a carbon with 4 bonds around it. That means 4 electron domains. Therefore, the electron domain geometry is tetrahedral. And because all of these electron domains are bonding electron domains, the molecular geometry is also tetrahedral. If we have a tetrahedral geometry, the bond angle must be 109.5 degrees. So this bond angle over here must be closer to 109.5 degrees. So these should be our bond angles. Okay, I think that's it. So that covers that shows how to determine the geometry around atoms in a line structure. So the first step is to convert the line structure into a Lewis structure and make sure that all the atoms except for hydrogen atom has an octet around it. And then we use the valence shell electron pair repulsion theory, or how the electron domains arranged in the space to determine the shape of the molecule, the shape of the molecule around those atoms. Okay, and then that's it. I hope this helped, and I'll talk to you soon in class. Bye, everybody.